Alrighty, welcome back. Today we're looking at cubic models and their applications. Our learning intention is for students to be able to use cubic polynomials to model practical scenarios and solve real life problems. First up, some notes. Cubic polynomials, that's x to the cubed, or the 3, can be used to model practical scenarios. When we do so, it's likely that we will need to restrict the possible values that can be substituted into the polynomial. For example, if we're using a polynomial to model weight versus speed, we'll need to restrict the weight variable because we can't have negative weight. This is called a domain restriction, and we're going to look at domain here. Hide him for a definition word. The domain refers to the values of the independent variable, and that's the independent variable is normally the x or the horizontal axes. Important things for you guys to note while doing these. First of all, wherever possible, you need to draw a picture. It's really useful to model the problem with a picture, and can be worth lots of marks. When answering questions, sorry, it's a typo. When answering questions that say show that, you must not start with the thing that they are telling you is correct. And if that's not making sense, we'll come back to it in an example. Always need to express a polynomial in terms of one variable only, and again we'll come back to an example. And above all, please read and reread the questions to make sure you have answered the specific question that they're after. Alrighty, so an example. A rectangle storage container is designed to have an open top and a square base. The base has lengths x centimeters and the height is h centimeters. The sum of the dimensions, length, width, height, is 48 centimeters. There are a couple of things we have to do in this question. Firstly, express h in terms of x. We just show that the volume, v centimeters cubed, of the container is equal to v equals this. This is a show that question, as referred to up here. We looked at a show that question. We're looking at a show that question in part B. We need to state any restrictions on the values of x. So this is going to be a domain, This is going to be a domain restriction. We need to sketch the graph of v against x, and they're telling us here that there is a local maximum at 16, 4096, and then we need to calculate the dimensions for the container with the greatest volume. So what would the length dimensions, what would the length, width and height be, so that we'd have the greatest possible volume of a container. Now, I always really enjoyed answering these types of questions at school, and hope that you guys can do the same thing. So first up, before we even look at part A, B, C, D or an E, we're going to get into drawing a picture. So the first thing we need to think is, I need to draw a pic. So what we were drawing was a rectangle storage container. The base has lengths x centimeters and the height is h centimeters. So in my mind, if the lengths are x centimeter, then there's going to be a square because both the length and the width are going to be the same, x. The height is going to be h centimeters. So I need to try and draw this in 3D. I'll do that the best I can here. So this is our square base, and the length of this are both x centimeters, and this guy here will also be x centimeters. Our heights, as we come up, will be h centimeters. Try and draw those all the same length, and it's got an open top, but we don't really need to show that for the sake of this one. Alright, not too bad. We just need to put in, this guy here is h centimeters. So now looking at part A, and in part A we need to express h in terms of x. h in terms of x. How do we do that? We need to use the information within the question often to answer these questions. We need to also pull out prior information. So here we read the question. It tells us that the sum of the dimensions, length, width and height is 48 centimeters. That's our first important bit of information. The other thing it tells us is that the base has lengths x centimeters and the height is h centimeters. So what can we write? From that first thing we pointed out, the sum of the dimensions is 48 centimeters. We know that length plus width plus height is equal to 48. That's what it said. The length, the sum of the dimensions is equal to 48 centimeters. Now what we know is that the length and the width here are both equal to x centimeters, as our drawing shows. So we can change that to x plus h is equal to 48. Alrighty, we can collect our like terms, which means 2x plus h is equal to 48. And now we need to express h in terms of x. That means h needs to be the leading term. Excuse me. To show that, we can subtract 2x from both sides, and we'll end up having h is equal to 48 minus 2x. Right, we've just expressed h in terms of x. That's what that means. So this question A done. Let's just express h in terms of x, reread the question, make sure we've got it right. H is expressed in terms of x. There's a common factor of 2 there I've just spotted, so I'm going to say, take a common factor of 2 out the front, 24, take away x. Alright, part B. What was part B? Part B was to show that. So this is one of our show that questions. Show that the volume V centimeters cubed of the container is 48 squared, take 2x cubed. Show V is equal to 48, have to check again, x cubed, x squared, take x cubed. Alrighty, so now when we're doing show that questions, one of the things that we need to do is draw on our prior knowledge. Alright, we need to use a bit of common sense. We also need to, as it says here, is we must not start with the thing that you're telling, the thing they are telling you is correct. Alright, so we cannot start with this guy here. We can't start there. Alright, so a bit of common sense, a bit of prior knowledge. What do we know the volume of a cube to be in general? Well, this is a volume of a cube. Hopefully we'll be able to say that the volume of a cube is equal to the length times by the width times by the height. And that should be common knowledge to us by now. Alright. Now we also know that the length and the width, another way of expressing length and width in this question, because of our drawing, x is the length, x is the width, so we can say L is equal to x, W is equal to x, and H is still equal to H. Alright, so let's collect these last terms. X times x equals x squared, so that's equal to x squared times by H. So we're getting somewhere. I look over here, I see an x squared term, I see our v term, maybe we're getting close to being correct. Alright, I look at this and I see there's a v and I see there's an x. Alright, there's only one variable in the polynomial. That was one of our things to note up here as well. Always express a polynomial in terms of one variable only. Right now, this polynomial over here is expressed in two variables, x and h. We want it only in one. As it is here, only one variable. So we need to get rid of the h. How can we get rid of the h? Well, we're sort of given a clue back in part A here. H is equal to this guy here. So let's substitute this h into this guy down here. That means that v is equal to x squared times by 2 outside of 24 take away x. Alright, this is exciting for me because it looks like we're getting somewhere. I see now that we've got an x squared term, we've got an x term. That means we've only got one variable. That means v is expressed only in terms of one variable. So this isn't quite showing, I haven't quite shown that volume is equal to this, but I think we can rearrange this to get it to this guy here. So let's expand this and see what happens. So we've got x squared times by 2 times by 24 is equal to 48, and then 2 times by negative x is negative 2x. Alright, so then we need to expand again, well not expand again, but Oh no, it is an expansion because we've got this guy ultimately in brackets. So we need to go x squared times by 48, which is 48x squared, and then x squared times by negative 2x, and negative 2x, that'd be negative 2x cubed. Negative 2x cubed. And hey presto, we've shown that the volume is equal to this. I should put a box around that in the same way that I should put a box around this guy here. Cool, that's part B done. Looking on to part C. Alright, question C. In part C, what we need to do is state any restrictions on x. Alright, so we need to use again our common sense here, and I'm going to use the diagram to help me here. Notice how many times I'm using this diagram. What I'm looking at is that x obviously is going to be equal to 1 centimeter, or 2 centimeters, or 3 centimeters, or 4 centimeters, or anywhere up to, you know, a million or infinity, and that goes the same for this guy here. What x can't be equal to is negative numbers. We can't have a negative distance. In this case, it doesn't make sense. That goes the same for h. So we can start by writing is that x has to be greater than or equal to 0, and so does h. H has to be greater than or equal to 0. So this guy here, our first statement, is a restriction on x. X can't be less than 0. I wonder though whether h has any influence on the value of x. And the reason I wonder that is because in question A, up here, we said that h and x were related. So by changing h, we're necessarily going to change the value of x. So what that means is that we need to work out whether h has any influence over our x terms. So what I'm going to write is another way of writing h is by that expression that we worked out in part A. So 2 outside of 24 take x. So we'll write 2 outside of 24 take away x has to be greater than or equal to 0. What have I done there? I've just realized that h, which is this guy here, and I've substituted in another expression for h. Alright, so now we've got a cubic inequation, and we're going to need to solve that cubic inequation to work out whether there's any further restrictions on x, because we've already got one restriction, has to be greater than 0, but we're going to see if there's any further restrictions on x. So to solve this, we need to divide both sides by 2. It's going to cancel on the left hand side. 0 divided by 2 is still just equal to 0, so we'll have 24 on colour, hope you can still see that. 24 is going to be greater than or equal to 0 still. Both sides we need to, we can take 24, and I'm going to do this first, even though it might seem a little counterintuitive. We'll take 24 from both sides. I could have just added x to both sides. So we're left with negative x, or negative 1x, is greater than or equal to negative 24. Then to both sides, to get x by itself, we need to divide both sides by negative 1. Now I'm dividing by a negative, which means I'm going to need to swap the value of the inequation. So x is going to be less than or equal to positive 24. Because that negative and that negative 1 will cancel out. Alright, so now we've got two different restrictions on x. First of all, x has got to be greater than 0, and x has got to be less than 24. So the way that we state that as an answer is this terminology, which may be new to you, and it goes a little something like this: 0 greater than or equal to, less than or equal to x, less than or equal to 24. These signs always stay the same here, and what that means is that x is going to be between 0 and 24. We can look at these two things in isolation. The first one is that x is less than or equal to 24. That's what we just showed here. The second thing is that x is going to be greater than or equal to 0, because we're reading that the opposite way around. So x is greater than or equal to 0. And what we said was up here, x is greater than or equal to 0. And I'll leave those colours there so you can see, but let's put a box around it, and there's question C answered. Question D. From memory, let's just double check, because memory is not something we want to rely on. Question D is to sketch the graph of V. We've got a local maximum at 16 and 4096. Sketch v against x. Alright, to do that we need to x-intercepts. We would let v equals 0, not y, because our variable is v. That means we've got 0 is equal to, what is our equation? 48x squared take 2x cubed. 48x squared take 2x cubed. How is the best way to solve that? That's a great question. What I can see is a common factor of x squared over in this guy, and a common factor of x squared here, so I'm going to factorize and apply the null factor law. Let's take out a x squared, and then we'll have, in fact, no, we'll leave it at that, 48 take away 2x. That means that we can apply the null factor law, and we'll have x squared is equal to 0, or 48 take away 2x is equal to 0. I'm going to accelerate through just so we get it done, and that means that we've got a turning point at x is equal to 0, an x-intercept at x is equal to 0. It would also be a turning point because it's an x squared term, or we've got, and you can solve this yourself, but that would be x is equal to 24. So we've got two x-intercepts. Y-intercept, we let, well, sorry, that shouldn't be y, that should be v-intercept. We let x equals to 0, and that would mean that v is equal to 48 times by 0 minus 2 times by 0, which is going to give us a point at v equals to 0. We also need to know where our turning points are, and we're told that there's a turning point. Let's write it over here for now. Turning point is at 16,4096. If you're wondering where I got that from, that was straight out of the question. So we now need to go ahead and sketch that. Since I'm out of room, I'm going to move on to the next page, just to show you where all it's located. Let's go there, we're going to move over here. Right, so we're still in the process of sketching. We've got a point at 0, 0. We also had a point at when another x-intercept at 24, 0. Our v-intercept was at 0, 0, and we've got a point at 4, no, it was the turning point from the question. The turning point from the question told us that there was a point at 16, 4096. Right, so we need to sketch up our axes, and I'm going to just grab one that I prepared earlier. And there it is. A couple of points on this graph. I'm told there's a local maximum at 4096, so I'm going to put 4096 there. This is of course the v-axis, this is the x-axis. And our restriction now, x-axis is from 0 through to 24. So I know our maximum value is going to be 24. I've taken that from a previous question. That means that guy is going to be 12. And so marking a couple of points on that graph now, we know that there's going to be a point at 0, 0. There's going to be a point at 24 and 0. And there's going to be a point at 16, 4096. 12 and 24, halfway between that would be 16 would be, that would be 18, so 16 would be here, so we're going to have a point here as well. Now we need to sketch that. It's a cubic graph, it needs to be nice and smooth, we need to make sure we're paying attention to our lines. I remembered from before that this point 0, 0 would have looked like this. Comes down and touches at the x-axis and then goes back up again. And then we come back down and like that. Of course we don't need to worry about this guy here though, because we're not looking at that part of the graph. Now let's just have a look at the way that I've drawn that shape. That's pretty poor. I would probably lose marks for that shape here, where it's a bit wonky, and it's still pretty wonky here as well. We need to make sure that's nice and smooth. I'd also probably lose marks down around here as well. But we get the idea. So there's part D done. What I'd also need to do is actually label those points. So we need to do that as 16 and 4096. That's that point there. I just noticed that I probably lose marks because that turning point isn't actually at the maximum there. I've drawn that pretty wonky and non-symmetrical. We need to label that point there, which we have already, and then this guy here is 0, 0. So there's part D done. Part E, if we go find part E, is to calculate the dimensions of the container with the greatest volume. Now one of these type of questions is why it's so important to read the question and read it again. So part D, we need to calculate is the key word. Calculate dimensions. So let's read and actually think about it. It's one thing to read it, it's another thing to read it, to actually interpret it. Calculating is involving putting some numbers into equations. The dimensions. What are the dimensions? We need to find the dimensions, which are what? Length, width and height. Very good, I hear you say. That's length, width and height. L, W and H. L and W are both x, so we need to calculate x and h. I don't need to do any calculations for x, because what I can do is read off that the maximum volume is going to occur when the volume is 4096. When the volume is 4096, the x value is going to be 16. So I can say straight up that x will be equal to 16. Now I need to calculate what h is. How do I do that? I go back to an earlier part in the question when we were told that, when we found that h is equal to 2 outside of 24 take away x. Alright, x is equal to 16. What's h going to be? Let's plug it in and work it out. 22 outside of 24 take away 16. That's 2 times by 8. That's equal to 16. One thing I haven't done is said centimeters, which is the units. And that is that question answered. We've found the dimensions, x, which is equal to L and W, and then h, which is also the height. So when the cube, let's just think about what that means, when the container is a cube with side length 16 centimeters, we're going to have the greatest possible volume. Alright, to finish off, let's take a look at our definition, which is domain. So the domain is the value or values of the independent variable, often the x variable, and that was the case today. I say value or values because there might be more than one value. Today our values were between 0 and 24. Alrighty, we'll see you in class. Good stuff.